Hey everyone, welcome back to Code for Teachers. I'm Michael Taggart, and this is Chapter 6, Objects. In this section, 6.2, we're going to create a race, the Python 500, or 500,000. So this is a very simple lesson. We're going to build a race, and we're going to do so using object-oriented programming, building on what we've already done, creating the car class. So let's review car for the moment. It has a make, it has a model, it has a year. None of those are really useful for a race. What traits are useful for a race? Well, we need to know speed, the car's top speed, and we need to know its acceleration, how quick it can get to that top speed. There are other factors, of course, like handling or traction, shift time, all sorts of things that go into creating a real race simulation. We're going to simplify the simulation, of course, for right now. And so we're going to focus on speed and acceleration along with distance and time and those other things. But the car, in terms of its moving through time, we're going to focus on speed and acceleration. As I said, sometimes we simplify characteristics for a reasonable, if not accurate, simulation. So for speed, we're going to talk about miles per hour, and sometimes we're going to convert that to miles per second, or kilometers an hour, kilometers a second, if you use the metric system like a reasonable country. Now, miles per hour, speed is a rate, so we know we have to involve time in this consideration. Acceleration, similarly, is a rate of a rate. So it's a rate of change of speed, right? So we describe acceleration as how many miles per hour per second has changed, or meters per second, or kilometers per hour. How much it's changed. So again, time matters, and we haven't really figured out a way to simulate time yet. Before we get there, let's talk about how we would add speed and acceleration to code. The first thing we should do is pick our cars. I'm going to use two cars that I think are really fun to put against each other, the Dodge SRT Demon, which is the quickest street legal car currently in production, and the Tesla P100D. They have similar characteristics. Of course, one of them is an old school, big old muscle car and just pushing with raw engine power toward a very high top speed and a very fast acceleration. And the Tesla, of course, is an electric car using its unique properties, instant torque, things like that, to get to a top speed very quickly. Now, as it happens, cars have different acceleration rates at different speed ranges, and they're usually measured as like 0 to 30, 0 to 60, 0 to 100. So we're going to take an average of those just so that we have a single number that we can work with. If we were being more precise, then we could change the rate that we use based on the speed that the car was currently traveling, but that's more fun that you could have with your students. So for the Dodge Demon, based on the information I found, it's 0 to 30 acceleration. It can go 0 to 30 in 1 second. So that's 30 miles per hour per second, right? 0 to 60, 2.3 seconds. So that's 26.08 miles per hour per second. And 0 to 100 takes 5.1 seconds. That's 19.6 miles per hour per second. We take an average of all those rates. That's 25.22 miles per hour per second. That's our acceleration rate. I couldn't find as detailed information on the Tesla P100D, but we do know that it has a top speed of 155, and based on its 0 to 60 time, it has an acceleration rate of 26.37 miles per hour per second. Now we have the car class. We're going to create a new class called race, and it's in this class that we're going to describe time. We can't just tell both cars independently to go and see what happens, but we can create a race that contains the cars, and we can handle those cars moving through time. Although this car will not be participating. All right, let's jump into the code and see how exactly we're going to do this. All right, let's take a look at our race class, which I realize sounds weird, but nothing socioeconomically going on here. We're just writing some code. Our first line is our docstring. We're defining a race between two cars. And then we have from car, import car. As we've seen before, Python lets us import code from other locations, like import random. So what we're doing here is we're looking at the car.py file, which you remember from seconds ago, and we're bringing in the car class from that. Why not just say import car? Well, Python doesn't know yet that the car class, the car file, only has the car class inside of it. It might have many things like a truck or a bike or whatever else. We only want the car class. So if we just said import car, we'd have to say car.car every time we wanted specifically the car class. But because we only want that, we can say from car import car, and then we just have to say car whenever we're referring to the car class. Okay, moving on to race, because I'm tired of saying car. It's our race between two cars. Dang. Okay, the first thing we have is our init function, our constructor, and we have self. We have racers, which is a list. It's going to be a list of cars, and distance, which is going to be a float. So our race to get constructed requires a list of all of the cars that are going to race and how far they're going to go. And then we have, of course, self.racers equals racers and self.distance equals distance. And then a third property, which is not defined by the arguments fed to the constructor, and that's elapsed time. We're going to use a stopwatch here and figure out exactly how many seconds have gone past in the race, but we don't need to feed that through arguments. We know that the race begins at 0 seconds. The next method, tick, is actually how we're going to manage that advancement of time. And you'll also notice that we're using this new syntax here with this little arrow and then car. This is another kind of type hinting. Just like we do the colons and then list or colon and float up here, this type hinting with the arrow gives us a hint about what data type the function will return. And what we're going to do in tick is we're going to advance the race by 1 unit of time. We're going to say that it's a second, but if your units are correct, it could be any unit of time. Every unit of time that we advance, we're going to return from this function the current leader of the race. And what that's going to do is give us current information about who's on top so we can decide who's winning. And then run is going to be the main business of this race function. We're going to run the race. And we haven't implemented this yet, but we're definitely going to be calling tick from inside of run because we have to do that. I don't know if you could guess as many times, but it's basically until somebody has won, somebody has crossed the finish line. And you should be thinking in terms of loops already that do we know how many times we want to run, or do we know when we want to stop and what kind of loop we're going to be using? Okay, now we have the function, we have the class defined, but we need to actually create some instances of objects to get this thing working. So let's build ourselves a Dodge Demon and a Tesla P100D. So let's make a Demon, and remember we're going to use this type hinting, so we're going to tell it that's a car. Then we bring in car. And then we need the year, so it's going to be 2017. It's going to be a Dodge Demon. And its top speed is 168 miles per hour. We give that as a 0.0, just to guarantee that it's a float. And then we need acceleration, which was 25.22 miles per hour per second. Okay, and then the Tesla is going to be similar. 2017 Tesla P100D. Its top speed was 155 miles per hour, and its acceleration was 26.37 miles per hour per second. Now, if you're doing this with your students, I would highly recommend pausing for a moment and saying, okay, just based on what we know already about these two cars, who has the advantage over short distances and long distances? Because we actually do know that already. Right? Based on the Tesla's slightly higher acceleration rate over a small distance, the Tesla's going to probably win because it can get up to speed more quickly than the Demon can. But over a longer distance, we don't know how long that distance is, but over a longer distance, because the Dodge has the higher top speed, it should pull out ahead of the Tesla. All right. Now, let's make ourselves a helper function called cars and put the daemon and the Tesla inside of it so that we can have that to feed to our race function. Now let's make the race. So the race needs a list of racers, that's going to be cars, and then it needs a distance. Let's do 0.25, so that's going to be a quarter mile, classic drag race distance. Okay, and then we need to know the winner. Well, because we've written this such that race.run is going to return the winner, well, we can just say race.run. And then we can say print winner. All right, nice and easy. Now I've left these extra lines in here for clarity, but you don't need to do that. And in fact, VS Code's going to probably yell at me. It's yelling at me because I forgot to do type hints. I need to be consistent if I'm doing type hints. I can't do so willy-nilly. Very good. Okay. Now, this code will run, but it won't do anything because we have to implement these methods. Let's start with the run method. It's actually the easiest of them to implement. So let's see what's going on here. We need to advance time until someone crosses the finish line. So until someone crosses the finish line. Until is kind of like when or if or while. So we know that there's going to be some condition here. Let's create the condition and initialize it to false. We'll call it finish line. Meaning that no one's crossed the finish line yet. Okay. Now we're going to advance time as long as that is the case, as long as no one's crossed the finish line. We'll say while not finish line, which is another way of saying while finish line equals false. Those two statements are equivalent. I like saying while not finish line. Just a little bit more elegant or eloquent. So what are we going to do while the race is still happening, while the finish line has been uncrossed? Well, we're going to have to figure out who's currently in the lead. How do we do that? Well, helpfully, the tick method is going to tell us who the leader is after every second. So we can say leader equals self.tick. Okay, so what's up with that self? Remember that we're talking about an instance of a race, not the class itself. So when we call the tick method from inside of that instance of the race, we have to say, you're calling the tick method that's attached to yourself. And that's how we say so, self.tick. It's like a reflexive verb. So we say self.tick, and that returns the car that's currently in the lead. We haven't implemented that yet, but we will do so appropriately, and it's going to give us the current winner. And then here's what we're going to do. We're going to check if the leader crossed the finish line. How do we do that? You know what I'm going to do? I'm going to bring the car class over to the other side. So I'm going to split my view here so we can look at both of these files together. All right, let's take a look at the car over here. What do we have? We have the year, make, model, top speed, acceleration, current speed, and the odometer. That is what I need. See, the odometer is going to hold the distance for the car in question. So I can actually compare the odometer's reading from that car to the distance of the race. And if the car's odometer has met or exceeded the finish line, then I know I have my winner. So I can say, if leader.odometer is greater than or equal to self.distance, return leader. Now, that's kind of it for my run. I advance time as long as there isn't a winner, and then I return the leader. And that's it. I'll get rid of this pass here. Now, I have to get the tick method going next if I want to do this correctly. So this is kind of interesting. What do I have to do with the tick method? I have to advance the race by 1 unit of time and return the current leader. Okay. So the first thing I need to do is push the self.elapsed time. We'll say self.elapsed time plus equals 1. So 1 second has gone by. Now, we have inside of the car class an advance method, which we haven't implemented yet. That'll actually be the last piece. But that's what we need to do for each car inside the racers. So I need, if you heard me say for each, that should trigger that you need a for loop. So I can say for car in self.racers car.advance. So car here, this can get a little confusing, but remember that car here refers to the current car in the racers list that we're talking about. And so we're going to call the advance method on every car in our list. In this case, it's only the Demon and the Tesla, but again, we could have 1,000 lanes of a drag strip if we wanted to. Now, this is going to advance the cars forward, but it's not going to tell us who's currently in the lead. There are a lot of ways that we could do that, but to keep it easy for right now, we're going to do another quick loop with just an easy trick here. So what we're going to say is leader equals self.racers 0, meaning we're going to say, we'll start assuming that the first car in the list is the leader. And then we're going to say for car in self.racers if car.odometer is greater than the leader odometer. Just remember, I need to do a type hint here. Your car. Leader equals car. So put another way, we're going to start assuming that the first car on the list is the leader, and then we're going to check all the other cars anyway. And in fact, to make it maximally efficient, we'll say starting from 1 and moving on through the rest. If car odometer is greater than leader, then odometer, then leader equals car. So we're going to replace the leader that we think is there with the new leader if one of them meets or exceeds the one we started with. This is ugly. We're going to learn very soon much more elegant ways of doing this using functional things like fold and map, but for now this will work just fine. Of course, we can't finish until we return the leader. Cool. All right, just for clarity's sake, I'm going to fold that method up. And I'm going to do the same thing with run. Okay, now let's go over to the advance. This is where the really interesting work happens. How do we get this working? So we have to speed up the car, and we need to increment the odometer. This is interesting. So what we need to do is say self.currentSpeed. The first thing we're going to do is try to advance the top speed, try to accelerate if we're not at the top speed. So what we do here is if self.current speed is less than self.top speed, right? We're going to accelerate. So how much do we accelerate? Well, we're going to do self.current speed plus equals, and then this is where some interesting math happens. Remember that our units of time are in seconds, right? So every time advance gets called, we're thinking 1 second has elapsed. But our speed is in miles per hour. Our acceleration is in miles per second. So self.current speed is going to plus equal the acceleration rate. Self.acceleration. Now, how do we do distance? Self.distance, or the odometer, is going to have its miles, the speed at which the car is traveling can tell us its distance change. We know time too because it's 1 second, right? But remember that our speed is in miles per hour, so we have to modify the distance. We have to change the speed to the same unit, which in this case would be miles per second. So remember that we have to just do a little bit of division there. So self.odometer equals self.current speed divided by 60 divided by 60, right? Divided by 60 is miles per minute, and then divided by 60 again is miles per second. That advances the cars. Let's give this a run here. We've implemented all the methods that we need to, and see what happens. We're going to chapter 6. Well, what do you know? The Dodge Demon won. Now, we're not printing out a whole lot of extra information here. So we could do something like print race, or say for car in race dot racers. Print car dot odometer, and we see what happens there. And there we go. Those numbers are going to look really weird because they only ran, a little bit more than a quarter of a mile, right? 0.2925 or 28. But clearly this is working, right? Because our odometer stopped at the quarter mile. Now, let's go ahead and make it a slightly longer race. Let's go ahead and make it a mile race. The demon wins again. So I'll admit I'm surprised by some of these results, and I think I know why. We have a bug. And some of you probably caught it before I did, which is that we have self.current speed plus equals self.acceleration. We don't have anything normalized here, meaning that this could bump the speed above the top speed. So we actually have to have another check here. If self.current speed is greater than self.top speed, we're going to just max it out, self.current speed at the top speed. So this guarantees here that we never exceed our top speed. That's probably going to help these results. Yeah, there we go. Now the Tesla has a chance. Okay, so let's try this back at the quarter mile. See what happens. The demon is still killing it. Let's see what happens if we just experiment with this a little bit and really handicap the demon. Bring that down to 22. There we go. Now the Tesla has a chance at winning. So at least clearly the simulation is working. It's just that the demon is a whole lot quicker than I thought it was. It's impressive in our very simple simulation. Okay, this has been a lot of code and a little bit of troubleshooting, but think about what we have now, right? We have a way of simulating races between cars at arbitrary distances, and we can maybe decorate the output here a little bit more. We could, create, like in first place was this car, in second place was this car, as far down as we want to do, and just make it a little bit cleaner. But this is nice just to get the basic data out of the race so we can simulate all of these things. And think about the way that we wrote this code. We didn't have to do any weird thinking that was abstracted from reality. What we had to do was take reality and represent it inside of the code. But because we were using object-oriented programming, that process was really, really simple, right? We defined a car that had properties that we understood: top speed, acceleration, current speed, its distance. And we defined a race that had reasonable information that allowed us to work with it. Object-oriented programming is very powerful for this reason. It allows us to take real-world objects or phenomena and define them in code, run simulations, make predictions. This is the heart and soul of data science. And once you understand object-oriented programming, you'll start to think about things in object-oriented ways a lot of the time, and you'll think of ways that you could describe everyday objects in code and how you would write methods that would describe their behaviors. Okay, that's it for this week. You can read some more about EdTech and programming at theforeverstudent.com. You can follow me on Twitter at mttaggart, and you can see this code on GitHub at github.com/mttaggart. I hope you've enjoyed this. I'm Michael Taggart. Thank you for watching Code for Teachers.